Hi, welcome back. So this is the second week of the semester. So before we go to the UML, the detail of the different UML diagrams, I want to talk more about the presentation. So first, I want to remind you that it doesn't matter when you're going to do the presentation. Please finish all your presentation and upload your YouTube video by March 8th. So this is a hard deadline for everybody. And here I also give you a sample presentation. And this student in the previous semester, and she got an average grade. So we know the presentation. You need to come up with the intent, motivation, structure, and the consequence, and so on. So this information you can easily get from, you can copy and paste from the internet. However, what I focus on is your demo application. From the application, I can tell how much effort you put into this presentation. So that's the part I use to grade your presentation part. And this student got average, so you can use this one as a benchmark and compare with what you have done. Okay. So this gives you the outline of today's lecture. First, I will go through some OO basic concept: inheritance, delegation, visibility, signature, polymorphism, and this idea, this concept are from your previous OO courses. So if you're familiar with this concept, you can skip this part. The second part and third part of this lecture is about modeling, and especially we are going to discuss UML, the Unified Modeling Language, because we are going to extensively use the UML in our course. Okay, let's go to the first topic. Some basic OO concept. So this is not an OO course or UML courses, and so I cannot give you a complete overview. I can only pick up some the most important concept that we will use widely in our courses. And if you want to know more detail about OO and the UML, and I give you this two textbook you can go to for the more details. First, let's look at something very fundamental: classes and object. We know a class is a collection. It's a collection of themes or concepts with have some similar or same quality, and then we group them into a class. An object belongs to a particular class is often referred as an instance of that class. So we can use our lecture as an example, like course 476, you can consider as a class, and today's lecture you can consider as an object, as an instance of that class, and happen in certain time. There are two ways to extend the functionality of a class. One is through the inheritance, and the other is through the delegation. So we're talking about these two important concepts. First, let's look at inheritance. So inheritance allows a class to receive some or all of the quality from another class. Then the starting class is called the base, super, parents, generalized, and the inheriting class it can be called derived, subchild, and specialized. And sometimes they use interchangeably. Yeah, that's totally fine, but usually people use it using it in a pair, like a base, derived, super, sub, parent, child, generalized, and specialized. So they're using a pair, but if you want to mix use them, that's also fine. And then there's a special kind of the superclass is abstract class. Abstract class defined as what a set of related class can do, and usually act as a placeholder for other classes. And you may think the abstract class is very like an interface. However, the interface only define only define the method, only define the signature of the method, but abstract class can have some implementation of the class. The abstract class declare using the abstract keyword. It can have both an abstract as well as concrete method. However, the abstract class cannot be instantiated using the new keyword, and also the abstract class cannot be declared as final. Yeah. So, however, the concrete class can be defined as a final, and the concrete class can only have a concrete method. Yeah. In Java, even a single abstract method make the class abstract. So please, if you have a concrete class, then do not declare any method as abstract. Otherwise, you cannot instantiate the class. So this is an example of the inheritance. So here we have a person is a base class, and then we have employee is a derived class. So this is a class diagram shows that the name of the class and the attribute and the method. And here this one method looks slightly different from the other. Is the get. Let me see. It's the get job. Yeah, because get job you see that the font is different. The font is a little different, but if you look closer, it's different because this method is declared as abstract. Then go to the implementation. See this abstract. So this one method is abstract. So this implies that the whole class can be abstract. And then we have a more specified class was the subclass employee. Is a kind of person. Because the inheritance used to describe a kind of relationship. So here we can see that the employee is a kind of person, is a special person. And here is an override the get job and implement the get job. And then the employee can also use the make job and the get age as it is. If employee doesn't override the make job and get age, and then the employee can use these two methods as it is. Delegation is another way. So we have the inheritance to extend the functionality of class, and we have another way called is a more common way to extend and reuse the functionality of a class. So so the delegation is more like a peer relationship. So here, delegation is more like a use relationship or peer relationship, and inheritance used to capture the kind of relationship. So this give you an example of using the delegation. So here the real printer is the delegate, and the printer that will use the method in the real printer is called a delegator. So in here first, the delegator printer declare a reference variable, a reference variable p for the real printer, and then delegate is print method to real printers printer method. So this is an example of using a delegate. So we'll see that this is very very flexible when you declare an instance variable point to the delegate, and then you can just use it. And as long as this print method is declared as a public, then you can use it. If this print method is private, you cannot use this way. So this going to our next topic is visibility. Visibility. So we're talking about visibility later. Let's see the delegation and the inheritance applied to our design pattern classification. So here we have two ways to classify. One is through the purpose that we already discussed last week, and another way to classify them is in terms of the implementation. So how you're going to implement this pattern. If you're using the inheritance, then we call it class. You're going to use class and subclasses. Then this like the factory and the adapter can also use inherit. inheritance, interpreter, and the template method all belongs to this category. It's going to use subclass. You're going to use inheritance to implement. And for the most of the rest of, for the rest of the patterns are all using the delegation, So this is by using this peer relationship to extend the functionality. Okay, so when we're talking about the delegation, we're talking about this visibility. So to use the method from another class, and that method has to be declared as a public. Uh, public or protected. It cannot declare as a private. And then we see the differences of these three visibility. The public is anything can see it, can use it, and the protected, there's only object of this class, and the derived class can use it. So in our previous example, if there's a printer and the real printer and the printer, they are not this have this derived the relationship, then they can only use like the public method. If they have this hierarchy, the inheritance hierarchy, and the method in the base class can be declared as a protected. And private is the most strict data hiding, and only object from this class can see it. So we have a 3 level of visibility, and then we see this how visibility changed over the hierarchy of the divulgation. So basically, this visibility can only get stricter and not otherwise. Yeah, for example, like if the member in the parents class declare as a private, and then it will be always private regardless of like a subclass may declare this again as a public, but still the private because it's a parents. The main class declare as the base class declare as a private and be always private. And the protected, we can use a similar strategy for protected. It can be protected or private in the subclasses. Yeah, it will be private if in a derived class if you use private, and will be protected. Will still be protected. However, it cannot be public. And then the last one is a public, and then if the base class declares a public, then it's up to the derived class. It can be public, private, or protected. So you will see this privacy. You see the visibility can only go up, cannot go down. Signature. Signature is used to distinguish one function from another. So for any method, there's a signature to tell the differences of the method. In C programming language, every function has to have a different name. So this one in C language is very strict. In Java has more flexibility because Java is an old language and it allows polymorphism. So it's demand for more flexibility in the signature. It can different. Two different methods have to differ in name. If they're not different in name, they must be differ in the number or the type of their parameters. For example, like this full. They share the same name, however, they have a different number of parameters. They are different, and this is not allowed in C language. But for the Java, they consider they're different. And then for the second example, they are the same because their type is the same. Even they use a different parameter name, however, they are considered the same. And the third one, they have the same number of parameter. However, the type of the parameter is different. Then they are different. And in C++ language, the signature also include the return type, but in Java doesn't have this flexibility. So this gives you how to differ in the signature in the old language. And then since we have this signature, then come to the next concept is polymorphism. It allows this you give the two different methods the same name. Then this give you the polymorphism. Yeah, polymorphism means many shapes. This implies that the method can take many different formality. So like here, like these two are considered as different. So there's two kind of polymorphism. One is the overloading. Overloading, like in our previous example here, this considered as overloading. Overriding is replacing inherit method with another having the same signature. In our previous example, like employee and person, you see that they get a job using a different implementation. Or implement the abstract method. So that's called overriding. So overloading is like a two method with two different names. So here I give you an example of we have a myPrint, and these two myPrint are two different methods. In Java because their parameter type is different. The reason we're using the overloading is so this gives you the programmer the flexibility of using the same name. Yeah. So here, if you don't use this overloading, then you will have a myPrint integer, myPrint double, and myPrint string. So here is a very it's kind of annoying. And in here, by using this polymorphism, the myPrint, they all consider myPrint. And then from programming point of view, then you can put whatever in here. Then the Java will recognize which method to use. So it's very convenient. Very convenient using this overloading. Okay, the next topic is software model and the UML. So first let's look at software model in general. So what is model? So before we build the real thing, we first build a model and then learn from the model and analyze the model, and the model can also drive the implementation. For example, here before we build a bridge, and we have a bridge design on a piece of paper. It shows the measurement of the bridge, and then in here, starting from here, people can do the analysis. And of course, this is considered as a statical model, shows the structure of the bridge. There's an other model can show different aspect of the bridge as well. So each view to a bridge is considered a different model. Then what is software model? Software model is a description of system which abstract out the irrelevant detail. So based on what kind of view you want to have, so you just remove the irrelevant information and just present what you need, what you want to have in the model. So how a model can be used? There's three ways to use a model. The first one is the analysis. Analysis model, so that you can detect the error and the missing in design before you actually writing the code. And also you can use the model to communicate with the stakeholders. Think about like each model represent the unique view of the real product. So different stakeholders have a different view on the product, and you can use the model to communicate with them. For example, like the use case model, you can use the use case model to communicate with customer and to come up with the requirement specification. And the model can also drive the implementation. Right? Yeah, like the class diagram, you can directly generate the source code from class diagram, and you can generate like the test cases from the interaction diagrams. So these diagrams can help us to drive the implementation. Then let's look at UML. UML is one of the software modeling language. So the UML stands for Unified Modeling Language. And before UML became the industry standard, and back to 1980s, there were many models fighting the method war, the so-called method war. Each warrior developed his own approaches to software system and engineering design, and UML is the legacy of the method war that occurred as a fusion of several competing methodologies. And here give you the UML 2.0 diagrams in which the red color represent the new diagram in the UML 2.0. UML has two major generation, UML 1 and the UML 2. So the red color represent the new model in the UML 2. So in general, there are two categories. One is to describe the structure of the system, and the other is to describe the behavior. So behavior here talking about dynamic behavior of the system. Structure has a class diagram, is the one we use the most often, and component diagram, composite, object, deployment, the package diagrams. The behavior, talking about different dynamic behavior, different kind of dynamic behavior of the software, the activity, use case, state machine diagram, sequence, interaction overview, communication, and the timing diagram. So we only focus on a few of them that we will use in our lectures. So these are the diagrams we will discuss in our class: the use case, class, sequence, state chart, and activity diagram. So use case diagram describe the functional behavior of the system as seen by the user. So this is from user point of view, what kind of functionality the software provide. And this one is particularly useful when you communicate with customer, because you as a developer, you have a solution domain knowledge, like the design software, the concept of what kind of database you use and what kind of architecture, the hierarchy of the system design. So all kind of solution domain knowledge. However, the user may not have this knowledge, but the user has the knowledge of how system should function. The functionality from the surface. So how to bridge the gap, and the use case diagram can become the bridge for you to communicate, so that you can get what the user really want, and then you can use this one to come up with the requirement specification. And class diagram describe the statical structure of system and consists of the name of the class, the attribute, and the association. This is one of the most used diagrams, and we will use this one extensively in our following in our future classes. So this one describes the structure can be used in the very earlier phase, and all the way to the detailed design phase. We can use class diagram to describe the structures. And then sequence diagram describe the dynamic behavior between actor and the system, and between object of the system. So this one, we will use sequence diagram to describe the interaction between the participant. So a participant of a structure. For example, in our the design pattern, we have different classes and come up with the overall design of a pattern. And then how this pattern structure can actually have certain functionality done. Then we can use a sequence diagram to illustrate how they communicate with each other, how they send the message back and forth, so that eventually we got the result what we want. So here we can use the sequence diagram to do that. And also sequence diagram, if you look further, is a perfect example of a test case. Yeah, so when you write a test cases, you can use sequence diagram. It tells you what a message is sent by an object and what message is returned. So here you can write a program to do that. You can use a test case to do that. So this you can automatically generate a test case. So you can generate test case from the sequence diagram. The state chart diagram describes the dynamic behavior of an individual object. So the object become quite complicated, contain a lot of attributes and the method, and then you want to tell when you call one method and fit in this method with certain attribute and what's the change of other attribute. So you want to see, the dynamic behavior of one object. You want to give a closer look of a detail of one individual object. Then this state chart diagram is the candidate. You can use that one to describe the different states involved in an object. Activity diagram model the dynamic behavior of a system, in particular the workflow. So this diagram, based on my observation in the past classes, I know most of students are familiar with this kind of activity diagrams. Use this one as a workflow and to describe the messages between object work across the use cases, and to use this one to describe like a certain formula, certain logic of the system. So we can use activity diagram to do that. So this one gives you the use case, what the use case diagram looks like. So here the use case is all the use case is within a box, within the boundary. So this is the boundary of the system, and then the actor is outside of the software system, but it will interact with the software. So each oval shape is a use case, represents certain functionality. And here is from user point of view. So the actor are the users, are the users or the outside environment that will interact with the software. Class diagram represent the structure of the software. Each class comes with 3 components: the name, state, the name, attribute, and the operations. And then the line between classes is association. Association is the relationship of these two classes. There are different kind of relationships, and we are talking about that relationship in very soon. The sequence diagram represents the behavior as interaction. So here usually start with an actor starting from the outside of the system, and here are the messages. So each message is actually a function call. So when you call this function, and this will trigger a chain effect, and then eventually, eventually what you get as a return, as a response of this initial function call. So from here you will see that the sequence diagram is going in vertical in a time sequence. So this press button 1 happen first, and then this will trigger this watch object called the blinking hours of this LCD display object, and so on. State diagram represents the state and the transition. So each box here is a state. You usually start with the initial state and end up with a final state, and then the event is a trigger. The event trigger the state change from one to another. So these changes is called is called transition. It's called transition. So this implies that when the object is in this state, and then when this event happens, this event is actually a function call. When you call this method, and when is the object is in this state, and then it will stop, go to the next state. It's called stop blinking. Yeah, stop blinking, and then finish after this state, go to the final state. So this is showing that the event is a trigger. Is a function call, but you will see that when you call the same function, well, the object in different state, it will go through a different route of the state. So this shows you that how this the relationship of different state and how they transition. Okay, let's look at so here I give you an overview of the software model, and the overview is 5 diagrams. Now we're going to go into the detail of each of them. The use case model. So we know the use case model represent the system from user point of view, or the external view, and we use this one model in the using during the requirement elicitation. Here we communicate with the customer. So here the use case diagram contains an actor and a bunch of use cases. So actor represent the role, that is a type of use of system or something of and anything outside of system that will interact with the software system under development. So it can be a user or can be the external, like another if you have external database, external system that will interact with your system, so that also considered as an actor. So use case represent a sequence of interaction for type of functionality. So on the surface, this use case is oval shape. If you use the enterprise architect or any UML tools, you double click on this oval shape, it will pump up a window, ask you to enter more detailed information. So that more detailed information is a key of the use case diagram. So the use case diagram is not just something looking from the surface. For example, like this passenger can purchase ticket, but you don't know what activity and what sequence of activity happen inside. So that's what we are talking about. The next. Yeah. Okay. So yeah, before we talking about detail individual use case, first we already talking about the actor, can be user, external system, physical environment, and so on. So a use case is not a simple oval shape. It consists of a name and participating actor, entry condition, flow of event, exit condition, and special requirement. So this is what happens when you double click on this oval shape. It pump up a window, and you should enter this information into that window. Yeah, into that window. So in here, in which the flow of event is the meat of the use case, is tell actually what happened, and entry condition is the initial condition of this. Is like when you declare an object, you give the initial value of instance variable. So this is very much like this. And the entry condition would for example, here that to purchase ticket, what's the entry condition? The user must have enough money. So that's kind of the entry condition. Flow of event, and then user follow certain step and exit conditions. The user has the ticket on hand. And a special requirement used to, and this one is very important. Yeah, when we discuss with the customer, is there any special requirement like how long does it take, and like the timeout, where this is particularly the timeout, or like when the user click on certain button, and what's the response time? And so on. So this we call it non-functional. This can be the initial non-functional requirement come from this we call this any special requirement for each use case. So when we discuss with customer, don't forget talking about this special requirement. Otherwise, later on, when you're asked to provide a non-functional requirement, and that will shape your architecture design. Then if you don't ask in the first place, you may have the idea later on. So it's better to ask now when you have this use case, because this one is to communicate with customer directly. You want to know what the customer actually want. Okay, in our previous example, the name is a purchase ticket, the actor, the passenger, entry condition, the user, standing in front of ticket distributor, and the passenger has enough money. Exit condition is the passenger has ticket, and here is event flow. So this information you need to get from, you need to discuss with customer what actually do, what so what user actually, also what actually inside the machine doing when this happens. So passengers select the number of zone to be traveled, and distributor display the amount of due, passenger insert money, and the distributor return changes and give and issue tickets. So these are the events. And here there's two relationships involved in the use case diagrams. One is extend and the other is include. So first let's see the extent. So in the previous example, we see that this event flow is a concrete usage of the software. This we don't consider any exceptions here. So, and the extent relationship represent exceptional or seldom invoked cases. For example, like what if a machine out of order, and what if the customer hit the cancel button? Hit the cancel button in any step. The user can hit the cancel button. And what if the machine run out of change? And what if like a user stand too long? Pause too long in certain step, watches the passenger just walk away, and operate just select the zone, then the passenger just walk away and forget hit the cancel button, and what happens? So you have a timeout. So here we all called exceptional cases, and they used to add to a normal usage of the system. So these are the extended relationship. And then the include relationship represent that one use case explicitly include the behavior of another use cases. So here is when we have multiple use cases. In this particular example here, the passenger can purchase different kind of ticket. Can either take a single ticket, a multiple card, can also purchase like a weekly or even monthly passes. And then you have you analyze this use case horizontally, and you find out all use cases contain one common activity. That's to collect money. Then I can factor that activity out to form a new use cases, to form new use case. And the reason we do that is to increase the readability of use cases, and also usually the use case is the starting point of the design. Then so each use case and is likely to become a component or even subsystem or certain function of the software. So here, this collect money, then we can delegate, we can use we can have a model, we have a component just to deal the collect money. So here give you the summary of the use case diagram, represent the external behavior, and are useful as the index into the use cases. And in here, the use case description, especially the flow of event, provide the meat of the model, not the diagram. The thing you look on the surface, that only tell the overview of the use cases. You need to go into individual use cases to look at the flow of event. Okay, the next one is a class diagrams. Class diagram. So class diagram represent the structure, and then we can use in different phase of the life cycle during the requirement model, the requirement analysis, system design, architecture level, or detailed design to individual subsystem or component. We can use the class diagram in all. I mean, in all the design and analysis phases. So a class contains name, attribute, operation, and for the operation, we need to give the signature, to tell the return value and the name of the attribute, the name of the method and what included, and what parameter and the parameter type included in the in each operation. And also class diagram, you can define the visibility. You can define visibility for the attribute and the method. In here, the plus sign means public. Yeah, we use the plus sign for the public and the minus sign for the private and the pound sign for the protected. So here is we can define visibility in class. And also for any UML diagram, not just a class diagram, you can add a node. So here an example of class student, and here the GPA. So here the node shows that this attribute contains the GPA of the student. So as I mentioned, the class diagram can be used in different phases. In the earlier phase, we call it domain level. We can have a domain level class diagram and just show the names of the classes. So this is in the very earlier phase. We don't have much information about the software. Then we can have this domain level class diagram to show the overall structure of the software. So here happened during the requirement analysis. And then in the architecture design level, we can have the subsystems. We can have subsystems, but sometimes we for the class diagram we show the attribute and what information is included. In each class, but we don't show the method. Yeah, because at that time we still don't know what operation each class will do, but we know what kind of information is provided. So it's not just a name. So the name is it tell what is it, and then we have the attribute tell what more information other than name this class provide. And then in the detailed design, will include everything. Yeah, so this one is right before we commit the resource to write the code. So this before we write the code, we have this domain level class diagram contain everything, not just the name, attribute, and the method, but also the relationships. So here we have a detailed relationships in the design level class diagram. So our design pattern structure, we are going to use the design level. So basically you have everything in here. Class interface. An interface is a collection of operation. So in the previous slides I show you the abstract class. So I mentioned there's a the similarity between the abstract class and the interface. The interface is just collection of operation. But the abstract class can contain the operation, can also contain the attribute, and even you can implement some of the method in the abstract class. But the interface just defined operations, and then it's rely on the classes to implement that operation. So two kind of requirement is in the UML. In the UML, there's a provided interface and the required interface. Provided interface are the interface that a class can provide to the client, and the required interface are the interface that a class need to fulfill its duty. So to fulfill my duty, I required a certain interface. To be more specific, I require some method. Yeah, some method from different interfaces. So this is an example of the interface example. So here we have interface is a collection of operations, and then this data class will realize. So this relationship is called realize. We'll implement this operation, the operations in the interface. So in the source code, when you have the keyword interface, then I know this one, the address IF interface is the interface define a bunch of operations, and then we have another class implement. You see there's a keyword implement this interface. Then you will see for the method here there's a implementation. Then this gives you the relationship summary. In the past, I show the realization is to implement, and I show you the association. Usually, the association is two directional, and the association can also have one directional. So if the one directional, you see this is open. It is this arrow. It is arrow. And here you have a dependency. So this also happened in the earlier phase. We notice two class has kind of relationship, but we don't know exactly what kind of. But we know that one depend on the other. Then we can define this dependency. Yeah, dependency is very general and high level. And the aggregation and the composition, they are related. So this composition is a strong aggregation, and they both describe the whole and part relationship. One is to mean the on, and the other is composed of. They're very similar, but I will tell the differences when we get to the point. And generalization is to describe the inheritance, describe is and is kind of, and the realization we're just talking about for the interface. So the association is the most often used relationship used to describe the the peer relationship of two classes, and the instance of these two classes involved in association will communicate in the real time. And how they communicate, just hold the reference, hold the instance variable. You have instance variable, hold the reference to another class, and then you can call the method in that in that class. Basically, that's how you that's how it happen in the implementation. Aggregation indicate a whole part relationship, and one component is comprised of many different parts. And in here, if you destroy this whole class, and it will not destroy the part class. So here it shows the class A owns class B. So if you destroy class A here, the class B still exists. And here give you an aggregation example. So in here, the order, you can see the order contain different part. The order contain shipping information and the product and the building information. So this all, I mean, a part of order. The composition is a stronger form of aggregation. So the only differences of these two is one, you destroy A, and you will destroy B as well. Okay, so here tell you that from implementation point of view, if you do the reverse engineering, you will lose. So you will lose some. You will lose the relationship because you cannot tell from the implementation. These two relationship is association or aggregation. So for example, like from the source code, we see that this car has a container instance variable engine, and then you know that this two has an association relationship. Just by looking at the code, we know that. But if you put in the context, then you know the engine is part of car. So actually, this two is an aggregation relationship. So from source code point of view, if you don't know the context, you don't know then you may consider them as association. So there's nothing wrong. Yeah, they are association, but if you put in the context, you know that the engine is part of car. They actually is an aggregation. So this example show you that when you do the reverse engineering, there's some tools that enterprise architect can generate the class diagram from the source code. But if you do that, it will not tell you, or if you give this code to the enterprise architect, ask to generate the UML class diagram, it will generate the car and engines association. You won't generate the second, tell you they're actually aggregation. So this aggregation, you can only get this information when you do the greenhouse engineering, starting from the beginning. Starting from having the class diagram showing the relationship. When you do the analysis, then you know, their aggregation. Generalization indicate a parent-child inheritance relationship between two classes and used to describe a kind of. So this shows that class A is a kind of class B. So class B is a base class and the class A is the derived class. So here we finish the use case diagram and the class diagram. The next is sequence diagram. Sequence diagram focus on time ordering of a message. So here you have the stuff from the actor send the message to the interface object, and this message is actually a function call, and then follow this time ordering. So the time ordering going down vertically. So here the select zoom happen first, and then insert the corn happen next, and so on. The sequence diagrams, as I mentioned, start from the actor, and then there are three kind of object involved in the sequence diagram. This boundary object we also call the interface. The boundary contain the user interface so that the staff can interact. So this boundary object has this vertical line. So it's a circle with a vertical line. And this is a circle with an arrow, with open arrow. This one is called a control object. So the control object used to coordinate between the object. So this one is more like your brain, like your nerve system, to do the analysis and coordination. And the third one we call the entity, contain the data. So you consider this one is more like a data warehouse, like a data. So all these objects contain the data. So it has a horizontal line. So usually for any sequence diagram, we have these three kind of object: boundary, control, and entity object. So in this particular example is for the staff member to create a contact in the in a database. So here you have this contact is like a object containing information, and then this view contact list and edit contact are two user interface object. So so here you can consider the view contact list is a window contain existing contact, and then contain add a new contact button. If you click on that button, it's like you send a message, create contact. So this implies you call this method, and then the contact manager. The contact manager is a control object, is to coordinate between the interface and the data. So the contact manager sends that the user try to create a new contact, and then it will open a new window. So from user point of view, is that okay? When I click on add new, and then I get another new window asking me to enter detailed information of the window. So from user point of view, you just see these two windows, but behind the window, behind these two windows, there's another object used to collaborate, used to coordinate this object coordinate. So this is from a user won't have this knowledge, but as a developer and then you have the knowledge, you should know that things not happen just on the surface. Just I mean, the transition between the interface, there must be something behind to coordinate. So that's a control object's job to do that. Okay, so pump up a new window, and for the user to enter the contact information, the name, the address, and so on. And then after the user finished, and there's a save. So this one, imagine you can associate it with a save button. So the user can click on save button. So and then save contact. So the contact manager knows that okay, this one I try to save what user entering here, and then call database interface. So in here you have an object containing data, and then why we still need a data we call the persistent manager. The reason is so here we abstract out all the management for data method, and then we put them in one control object. So this object is responsible for save the data, to query the database, and to delete, so to do all kind of data management. So here we put in one object. So this one called a persistent manager. So make persistent, and this object will insert the contact into the entity and entity object. So from this one is a very typical example. Involves three object, entity, control, entity, control, and the boundary. So here the UML sequence diagram represents the behavior in terms of interaction, and this one is useful to find the missing object. In the previous example we show here, because each sequence diagram must contain three object: entity, boundary, and control. And usually the control object is the one people will forget in the first place, because this one is not intuitive. Yeah, it's something you need think deeper in thinking deeper, like how they cooperate. Then you may come up with some control object. So usually the missing object is a control object, and it's very time consuming to build, but worthwhile. But worth the investment. And this one will complement the class diagram, because class diagram just show the statical structure. Then this one will show the interaction. We'll use the sequence diagram when we describe how the participant of the design pattern communicate with each other, and that's perfect to use the sequence diagram. Okay, the next diagram is the state diagram. So state diagram is also a dynamical diagram, but this one used to describe the sequence of state and the object goes through in response to external event. So external event is a function call. One call the function inside this object. Then when this is the object in different state, and then we'll trigger the state change. Yeah, we already talking about this example. It shows that initial state is blinking hour. It shows that is our our attribute. Our attribute is about to change. So when the hour in this state, if this button to press, if this method is called, then this hour attribute will increase by 1. I mean, here will increase by 1. And if in this state the button 1 is pressed, and then this hour this hour variable is set, and then this minutes attribute is about to change. Yeah. And it's in any of this state, if button 1 and 2 press, if this method is called, then the time, all these three variables are set. Yeah, so we stop blinking means we set these three attribute and then exit. So state chart diagram are used to present the non-trivial behavior of a subsystem or an object. Yeah. What's the difference of interaction, the sequence and state? Sequence diagram involve multiple objects, but this state diagram has contain only one object. The last diagram is activity diagram. Activity diagram shows the flow of control, and here we can use this one to describe the flow across use cases or flow of a complicated use case and the logic and of algorithm. So here is each node here, each box here is an activity. So there are different nodes. Yeah, the initial node, final node. There's two kind of final node: activity final and flow final. There's a fork node, join node, merge node, decision node. Let's see each of them. The initial node is this one is. I mean, this applies to all like that dynamic UML diagram. The start. Yeah, I mean the initial node is a dot. Yeah, is a dot in black. The final node is a dot with a ring, and the flow final node. So here, since in the activity diagram, you will see there's different branches. It can go different branches, and if one branch goes to the end, we call this a particular flow goes to the end. But I mean, the entire activity, if you take different branches, it will still go on. So this is not the final of the entire activity, but it's just certain flow goes to the end. If that's the case, for certain flow, we can have this flow final node. And the fork and the join node, they look exactly the same, and we use this one to describe the concurrency. So we can have parallel activities. So then send this fork and join, they look exactly the same because this is talking about the starting of the concurrency is a fork. And when this concurrent activity happen, and then eventually you need to synchronize all the event, and then you have this join node. So just by putting here, you cannot tell it's a fork or join, but when you put in the context, when you put in the diagram, then you can tell which one is a fork and which one is join. And similarly for the merge and decision node, they look exactly the same. The decision node is like a if and else. If you have like in the if and else and else statement, it is you are making a decision here. If yes, I go to one branch. If no, I go to a different route. So this is a decision node. And the merge node is more like it's like a come and go. So you have a different activity flow coming in. So first come, first go. There's no synchronization is needed, is required here. Then we have this merge node. But the merge node and decision node, they look exactly the same. But when you put, as I mentioned, just like a fork and join node, when you put in the diagram, you can tell which one is a merge and which one is a decision. So first, let's look at the decision node. So decision node is like a if and else, and else then. So it's like an if and else relationship. So in here, when you so here we're talking about the instance management. When you open an instance, then there's three branches, three possible branches you can go. Depend on the nature of the instance. If the instance is a low priority, then we just put in a queue to allocate the resources, and then of course, we have a limited resource, so when this one comes, just put in a queue. And then if the case, if the instance is some building catch fire and it's a high priority, then we notify the file chief, and the file chief can intervene into this allocated resource, can override the queue, so put this one in the higher priority, so you can allocate the resource and come to the site immediately. And if it's not fire, it's just like a shooting happen, was something like a grandma and falling on the floor. For that kind of, we still consider as a high priority, but we don't need to, there's no fire involved. And we notify the police, and the police chief can allocate the resource. So from here you see that this activity diagram can describe these different scenarios. Yeah. By using the decision node. And the activity diagram can model the concurrency. So here when you open instance, then you have a 3 activity working on in parallel, allocate the resource, and you can coordinate the resource, and then you can document the instance. So things happen in parallel means there's no particular order. Yeah, there's no particular order happen, or you don't care about the order. Yeah, but then we can have this fork, so because of splitting, so here, so this node is like fork, so you have one in and a multiple out, and this multiple event happen at the same time. What time is doesn't matter, sequence doesn't matter, then we use this concurrent. And then this one is a join node. So you have a multiple in and one out, so the synchronization implies that you cannot go on to the next phase until all 3 finished, all 3 activity finished. Then you can archive the instance. In general, most of node in activity node are action node. It's taking an action. There's also in some occasion we have object node. Object is a product. Object is a product of certain action. For example, like here we write a CIS, and then you review CIS, and the product of writing CIS is a CIS. So the CIS is under review by a different person. So here, this object node happening. It's used to connect to action node. So this example shows you all the nodes involved we discussed so far. We have initial node, we have final node. So here is the order process activity diagram. You receive the order, then you make a decision here. This is a decision node. You make a decision here is reject order or accept order. If you reject order, then it's go immediately to closed order. So this one is a merge. So you can just go directly. Yeah, if there's nothing in front of you, you can go to the closed order, and then go to the final node. So this entire activity end. If you accept order, then you fill in the order information. Then we have a join, or no, we have fork node here. So this describe the concurrency. Yeah, so you shift order, and then at the same time, you send an invoice, and for the customer to make payment and to accept payment. So you have a payment and the shipping. This go in parallel. So in here means you cannot, the product cannot go out of the door if you don't have the payment. So these two must both finish in order for you to close the order. So here, then this node is the join node. And then between the send invoice and the make payment, we have an object node is an invoice. Invoice give to the customer for customer to pay to make a payment. So this implies that these 2 nodes involve two different users. Okay, so here the last slides give you the summary of UML. The UML give you a wide variety of notation for represent many aspects of the software. So each aspect represent a unique view into a software. So we only focus on few of them. Yeah, because we are going to use them in our class, or the graduate student, you will use this diagram in your term project. So we only discuss like 20% of them, I think, and 20% of the overall UML class diagram, for the all UML diagrams. But this 20% of the diagram we discussed today can solve 80% of your problem. So it's very productive. Just we only focus on a few important diagrams, but this will answer most of your need.